Melting, freezing, and sublimation. So think of a solid. As we increase the temperature of any substance, the particles move faster. In a solid, all they're doing is vibrating. But as the temperature increases, they vibrate more. And at the melting point, the particles have enough energy that they are able to break free from their rigid structure and they can slide past each other. They don't have enough to go off into the gas state, but they can turn into a liquid. And so we'll see the solid melt into a liquid. So here's an illustration of water in the solid state, and all the little water molecules are arranged in this open crystalline structure, and as it melts, they begin to move randomly among each other. At the melting point, provided that there's ice and water present, the temperature will be 0 degrees Celsius. Because as we put heat into the substance, into the ice, and increase the movement of the particles, the faster particles melt, the slower particles are still frozen. And as we put energy in, all of the energy goes to melting the solid before it goes to increasing the temperature of the liquid. And so you won't see a rise in temperature until all the solid has melted. And so we're going to see a similar energy curve for melting as we did for boiling. We take a solid block of ice at minus 20 degrees Celsius and we add heat. The temperature of the ice will increase until it gets to 0 and begins to melt. And at that point, all of the energy goes into moving these guys from the solid to the liquid. These liquid particles do not increase in temperature. And that will go on until all of the solid has melted, and then the temperature will increase. Melting is an endothermic process. It makes sense. You know, how do you melt a frozen, thaw a frozen steak? You don't really want to melt it, but how do you thaw something that's frozen? You could stick it in the sun, you can stick it in the microwave. You need to heat it up, right? You need to put energy into it. Why do we put ice into our drinks? To cool them down, right? Because warm soda is nasty. So we put ice in it. It makes it cold. How does it do that? As the ice melts, it absorbs energy from the soda and causes it to become colder. So melting is endothermic. Freezing, then, the opposite process, is exothermic. I don't know about you, but when I think of exothermic, I think of something that's hot, right? Burning something is an exothermic process that gives off energy, right? How is freezing something exothermic? Well, freezing is not a spontaneous process at room temperature. You don't see water just spontaneously freezing into ice, right? You have to make it freeze by pulling energy out of it, and that's what your freezer is doing. The condenser and the compressor in the back of your refrigerator is working pretty hard pulling energy out of the freezer compartment because freezing is an exothermic process. We're down in Tulare. I live in Reedley. So up in Reedley, we are surrounded by fruit trees, lots of citrus up there. Citrus, oranges mostly, they are on the trees in the winter. And we get freezes around here. And some years it's really bad and it damages the oranges and it's just really devastating to the local economy. And so farmers don't want their oranges to freeze. we can use this exothermic process of water freezing to protect the oranges. What they do when a freeze is predicted is they'll flood the fields with water. And so as the temperature drops, that water in the fields may begin to freeze. But as it freezes, it releases energy and keeps the temperature at 0 degrees Celsius, at 32 Fahrenheit. 32 Fahrenheit is an okay temperature for oranges. They can get down to about 26 before you really have to be concerned. So by having the water in the field and allowing the water to freeze, it moderates the temperature. And then they throw in some wind machines to blow the warm air at ground level around so the oranges at the top aren't freezing. So chemistry involved in growing oranges. Heat of fusion. So fusion is melting, and vaporization, students don't have trouble with that. Fusion doesn't really ring a bell. The way I think of this is, what happens when you melt chocolate chips? They fuse together, right? They turn into this one big gooey mass. Fusion is the scientific word for melting. So the heat of fusion is the amount of heat required to melt 1 mole of a solid. So melting ice, solid water, to liquid water, for 1 mole of that requires you to put in 6.02 kilojoules of energy. This is positive because it's an endothermic process. The opposite of melting is freezing. So this is the same amount of energy, but the sign is negative because the energy is moving in the other direction. So as water freezes, it releases 6.02 kilojoules of energy per mole of water. So that's another conversion factor we can use, relating moles of solid or moles of liquid and the amount of heat needed to melt it, or the amount of heat released when it's frozen. So here's an example. We need to remember that number though, 6.02. Calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So we've got 15.5 grams of ice, which is water. And they're asking us for amount of heat. So that's probably going to be kilojoules. We're starting with grams. The path here is going to be the same as for calculating the vaporization. We need to convert our grams to moles and then moles to kilograms, because the heat of fusion of water is plus 6.02 kilojoules, that's not a K, kilojoules per mole. That number wasn't given in the problem. You have to go look it up. So 15.5 grams of water, we're going to convert to moles of water and then to kilojoules of energy. So moles come down here, and grams are down there. Just kilojoules, that's the heat of fusion, 6.02. And 1 mole of water weighs 18.0 grams. We have 15.5 divided by 18.02 times 6.02. 3 sig figs, 5.18 kilojoules. Mastering chemistry I really don't like the way they do the sign on these things. They will use the sign in some areas, and then in other areas they use words. So this is the amount of heat absorbed If they're using a word that describes the direction, then they don't care about the sign. I think we should just, if we're going to use the sign, then we should use the sign and do it that way all the time. But heat absorbed, you're thinking about, I am the ice cube, I have heat being absorbed, that's like money coming into my wallet, this is positive. If we have water freezing, which is exothermic, then the amount of heat being released, if we just calculate Q, it would be negative. So that's going to be a little confusing, and I'm sorry, I will avoid that on exams. Any questions? So here's a diagram showing water from solid through melting to liquid. So here we have water that's frozen, and if we add heat to it, it will increase in temperature until it gets to the melting point. Temperature stays constant until it's all melted, then the temperature increases and until we get to the boiling point, and then the temperature remains constant until all the water has been turned into a gas, and then the temperature can rise again. Because of these flat places in this heating curve, water is really convenient. I mean, you can do this with other substances too, but if you want something to be at 100 degrees Celsius, you just place it into a boiling water bath, and it'll be 100. And you don't even really need a thermometer. You just know because it's boiling. If you want something to be at 0 degrees Celsius, you put it in an ice water bath. And as long as there's ice and water, you know the temperature's 0. And so it makes things really convenient. And that's why we often see things either at 0 or at 100 degrees Celsius. Sublimation. Sublimation is an interesting process. This is the physical change directly from the solid state to the gas state without melting in between. Doesn't go to a liquid in between. So what happens with this is that we have molecules on the surface of the solid leaving the solid. They are not held as tightly on the surface because what's holding these together? It's those intermolecular forces, forces of attraction between molecules, right? Well, something on the surface is not attached or attracted in all directions, just to the side and below. And so it's held less tightly, and it's easier for it to escape. So if you have particles that are on the higher end of the energy spectrum at the surface, they can escape directly into the gas state without melting. Dry ice. I think most of us have at least heard of dry ice. Do you know why they call it dry? Because it doesn't melt. If you have a cooler and you're going to a picnic and you had a bunch of sandwiches in there and you put regular ice in there, you have to take some precautions to keep your sandwiches from getting soggy, right? Because the ice melts into water and the water gets everywhere, even into the Ziploc bags that are not supposed to leak. Dry ice doesn't melt. At atmospheric pressure, it does not melt at any temperature. It just goes directly from a solid to a gas. It's frozen carbon dioxide. As it goes into a gas, it expands and leaks out of the cooler and just goes away. You never, ever want to put dry ice in a sealed container, okay? Because it will pressurize the container and can definitely explode, and that could be very dangerous. And, some people do stuff like that and they get lucky, but I'm officially telling you, don't try that at home. So, even at minus 78 degrees Celsius, which is really cold, carbon dioxide molecules have enough energy to leave the surface of the dry ice and sublime. Here's a picture of dry ice subliming. What you're seeing underneath here is not, this almost looks like a jellyfish or something. What you're seeing down here is the air being cooled, and cool air falls, and then this white stuff here is actually moisture in the air condensing because of the cool air. So it's almost like a fog. But dry ice like that, it will just slowly disappear. If you put dry ice in water, it bubbles, and then we see this smoky stuff coming up because it's cold, and again, it creates that fog look because it's cold and causes the water in the air to condense. Now, throwing some carbon dioxide in a pot of water or something, you could try that at home, but just don't put it in a sealed container. But people use that like at Halloween and stuff, mimic a boiling cauldron, right? It's not actually hot. It looks like it's boiling, right? But it's actually the carbon dioxide in the bottom of the cauldron going into the gas state. The bubbles come up, and so it looks like it's boiling, even though it's actually very cold. It's fun stuff. Regular ice will also sublime. It just doesn't do so nearly as quickly. Have you ever found an old tray of ice cubes in the back of the freezer? And what do those ice cubes look like? White. Yeah, they're all white, and they're small. How do ice cubes shrink? It's like, did somebody make miniature ice cubes in this tray? No, someone made regular-sized ice cubes, but they stayed in there for a long time, and sublimation occurs. So the water particles on the surface of the ice cubes are escaping into the gas state within the freezer. What happens in the freezer? You get frost buildup inside the freezer, right? Some of that comes from when we're opening the door and air comes in that has moisture, and that moisture from the air will then freeze on the sides of the freezer and cause all those ice crystals. But some of those crystals come from things in the freezer that contain frozen water that are subliming. In cold climates, I grew up in a cold climate, ice or snow on the ground will actually slowly disappear even if it never gets above the freezing point of water because it will sublime. And it happens in the freezer as well. I think I've got more. Yeah. So have you ever opened, say, a bag of tater tots or French fries? It's been in there a while. And you dump them out on the pan, and there's the tater tots, but then there's all these ice crystals. Like, why the heck would you want all this ice in here with your tater tots? Did they put that in there? No, they didn't put it in there. All that water was originally inside the tater tots. But the tater tots have been in the freezer for a long time, and the water within the food sublimes, and it gets into the gas state within the container, the plastic bag, but the plastic bag is sealed up, so the water can't go anywhere, so what does it do? It condenses and freezes again, and so we get these crystals. And the longer that goes on, the drier and nastier your food gets, and we call it freezer burn, right? You take a piece of steak out, and it's all like white and nasty on the sides, and you cook it, and it's just not the same. You could soak those things in water. It's not going to help because it came out of the food, and you can't get it back in there easily. 2 ways to avoid that. Here's just life tips. If you freeze below the normal temperature, a deep freeze, the colder your freezer is, the less freezer burn you're going to get. It will just happen slower. So that's why some people have these sub-zero deep freezes. The other thing you can do is you can package your food in a way that has very little airspace. So the vacuum sealers, they suck all the air out. So now the plastic is lying right on top of the food all over the place. That doesn't give the water anywhere to sublime to. So the water on the surface is in contact with the plastic bag. You can't really go anywhere. And so that will work even better to preserve your food. Any questions about that?